Good morning, everyone. Today we will continue to study real analysis in many variables, and specifically we will talk about zero measure sets, which is an introduction to kind of an introduction to measure theory. So we will cover the most important theorems that you need to know to really understand this subject. So here we have the first, the starting definition to get us on the, because for zero measures there's kind of a lot of definitions. I mean, one may consider the Lebesgue zero measure. I mean the Lebesgue outer measure, and which has a value of zero, and this is kind of equivalent. It is called zero measure or zero measure set, and yeah, it is totally equivalent. But with this, you don't really need to understand Lebesgue measures or any measure theory. We can start with this, and then we can construct the Lebesgue measure in the course of measure theory. So this is like the most basic definition that I can find to understand this topic. So the definition tells you that a set has an m-dimensional measure theory, or just a zero measure on or n measure zero, if and only if for every epsilon positive there exists a countable family which could be finite or infinite, but it is formed by open and bounded m cubes, such that it is a covering, i.e. this happens, and also the volume of the value of the series of those volumes is strictly less than the given epsilon. So this is an infinite sum, but if the countable family is finite, which can be also considered, this will be a finite series, a finite sum, and not a series in general. All right, so the first theorem tells us that we have some countable family here of any subset. We don't know if they are, if they are closed, open, or whatever, but it holds that every element of this countable family has n measure zero, and then we need to prove that the countable union of all of them has also n measure zero. So this is important because it is kind of easy to see that if we have a countable finite family of sets with n measure zero, then the union will it is relatively simple to prove that the union has n measure zero. Because if this holds for x1 until x, I don't know, x sub s, then you can define a countable family from the family that exists from here, right? And one way to define it will be to start counting here on 1, then this is s, and then this is s plus 1, and so on. So with this you form the new countable family. So it is clear that this can be done for finite families, but here we are with a countable family in general. So the idea of the proof, it is the following. We can choose one value of epsilon, let's say for some epsilon that is greater than, non-negative. We can fix some j in the natural numbers, or this is the natural numbers, which is arbitrary. And then we know that there should exist some family, some family that covers xj here, and that the series of the sum of those volumes can be bounded by any value, any positive value, and we can say that this is the value that we want, and this is valid because we were fixing j at the beginning, so this is a given number, right? All right, so it happens that when you make the union of all of those xk's, when you make this union, you can call this as simply x, and it happens that x can also be written as the union from, you know, so we are making those two indexes vary over the whole natural number from 1 to infinity, so it's just the union of everything, right? It's just a successive application of control unions. All right, so given that let's say that we have if we have some finite set in here which is finite, then there will exist some k in the natural numbers such that if this is we were with j is in f, then both j and k will be less than this given value. So this holds for every finite subset of this product, because this sets of index is in fact this product, right? We are just writing it like that. So this will happen because f is finite for any finite, and then we have that keeping in mind this arbitrary finite set, the volume here is less or equal than this here. And so the thing is that before doing this, we didn't know which how many of k's were, how many of j's were, but when you consider this fixed value here, you can make sums with the same upper bound, and it will hold that this is more or equal than the following, because volumes are always non-negative, so we can only have a bigger number here on the right hand side, and so this is strictly less than, this part here is strictly less than epsilon divided by j plus 1, because we were saying this here when we make k vary. This is k, so we are making k vary over this set, so this is less than this, and then given that we have this will be less than epsilon divided by 2, and this is so because the series of this series has j equal to 1 and k, this is equal to 2.5. All right, so we found that this is an upper bound of any finite sum. So when we take the limit of all of these of k0 so when we make this set arbitrary here, we can write this like that. This is perhaps an abuse of notation. Will be less or equal than, and this is less than epsilon. So when the least upper bound, or when the least upper bound is when this upper bound increases towards the plus infinity, this value of this sum of this finite sum will be less than this epsilon divided by 2. So in the limit it is less or equal than this value, but this is still less than epsilon. So that happens. And so we found our covering that could be whose sum of volumes could be minimized by arbitrary epsilon. So we have that this union has n measure 0. So that's proven. All right. So this is a technical lemma now. So here we have that V is a compact n block such that we have some countable family of open and bounded m cubes that cover this compact block, and it will happen that the volume of V is less or equal than the value of this series, which could be finite or infinite. I mean, it may converge or it may not converge, but in any case, this is more or equal than the volume of V. So here we will have that, given that V is compact and this is an open cover, then there will exist a finite subcover. So this is by the definition that we all know about compactness. So this can be covered by this, and then since this is a finite union of bounded m cubes, this is also bounded, so we can say that this is this is inside its closure, and this can be found inside another m block, right? Because this is bounded. All right, so it will happen by the definition and basic properties of characteristic functions, that the characteristic function of V is less or equal than the characteristic function of this sum of this union, and this is less or equal than the summation of the characteristic of this here. So you know that the volume of V is equal to here, because this is a block that contains V, and we saw this in the previous video, in fact, the video of the properties of Riemann integrals. And so this will be less or equal than, because inequalities of function are maintained when you take the Riemann integral. So this will be less than of this union, and this is less than the sum of those, but these are the volume of. So we have that proven. Well, and this is, I forgot the last step. This is still less than the sum of every cube, the volume of every cube, because this is increasing, because when you sum the volumes that we are missing, then it can only be bigger, right? Because volumes are positive or 0. So we have that, and this is for compact blocks, but we can do in fact a quicker generalization for this. So if we suppose that this is a bounded block, which may not be compact, could be open, could be closed, could be semi-open, and whatever, this is still true because the volume of V can be taken as the supremum of the volume of A, such that A is inside of V and A is a compact block. So this is our result of topology, which we can use. And so given that the supremum of those volumes is the volume of V, and each of these volumes is less or equal than, these, then the supremum will be less or equal than that's series. So we can generalize this lemma from compact sets to just bounded. This can be quickly done. Alright, so the next theorem tells us that we have a bounded block and it has n measure 0 if and only if V is a degenerate block. So the first that we will do is to suppose that that V has n measure 0. So we will look for a contradiction, and the contradiction will be that the volume, that V is looking for a contradiction, that V is not degenerate and has n measure 0. So if you remember, V degenerate means that one of its sides or edges is a singleton. So we are multiplying intervals with a singleton. So that means that it is degenerated. So degenerated blocks are the faces. If we are on R3, two degenerate block. This is notation. Two degen block can be taken as this face. It could be this edge. This is more degenerate. This is a one degenerate block, and the last level of degeneration will be just a vertex. So this is a 0 degenerate block. So in any case, here, for instance, here we are multiplying one singleton by two intervals. Here we are multiplying two singletons with an interval, and this is just three singletons multiplied. So this is the biggest degeneration. So if you recall what that the volume of V is equal to the product of the difference of each intervals, of the length of every interval. So this is clear. Then if it is not degenerate, this will be strictly more than 0, because every interval has some length here, right? This is obvious. But then, because it has n measure 0, then it can be covered by some family of cubes. So the second condition of n measure 0 will say that the sum of those volumes can be bounded to any value. So we can bound it by the volume of V. But given that this is a covering of V, this will be more or equal than V. So we got here our contradiction, because this real number cannot be strictly less than itself. So that proves this implication. And now for the other one, it is kind of clear also. So let's suppose that let's suppose that V is a degenerate block. So this part of the proof is can be taken as follows. So V would be equal to, because it is a degenerate block, will be equal to a singleton times some block, which we don't know if it's degenerate or not. So for the sake of the argument, let's suppose that this is a non-degenerate block. Otherwise, we will put outside every side of this block which is degenerate. But let's do it just in the case of one singleton times a non-degenerate block. All right. So given epsilon positive, we can define some block which is compact, that is like this. So this is compact. This is a closure of this non-degenerate block, and this is some closed interval, and this epsilon prime we will choose this value later, but for now let's keep it like that. And then it is clear that V is covered by the union of these compact blocks, and so V will be, the volume of V will be strictly less than well, this part doesn't really matter. It's just, let's just focus on this series. So this is Vj, and this is, well, this is equal then the volume of B prime, because this is fixed, times the length of this interval, which is epsilon divided by 2I minus 1. And so since this is a constant, it can be taken outside, and then the value of this summation will be 2 times epsilon prime. This is epsilon prime, so the result will be this. And then, given that we can give epsilon prime any value that we want, we choose epsilon prime as epsilon divided by 2 times or 3 times, if you wish, the volume of V prime, because V prime has a fixed volume. So this is why we say that V prime was non-degenerate block. If it has more a higher level of degeneracy, I mean if this is also degenerate and equal to this times B prime prime, so we will do the same but with another interval like that. So at any rate, we could even have done something more simple, because if you remember the definition of non-zero measure, I mean the definition of M0 measure, we have that this is a family of open and bounded M cubes, but it can be proven that instead of M cubes you can take M blocks, and instead of open it can be closed. So in this case, unbounded always bounded. But in this case, if you wish to have a bounded closed block, I mean, and this will be a compact blocks, then we could have just that. So suppose V is degenerate, so V will be equal to a singleton times anything, and this could be degenerate or not, we don't care, but this is covered by the closure of this times A, and the rest of the elements of the countable family can be the empty set, because the empty set can be taken as a block also, a block with the greatest degree of degeneration. So even then it is said that it is a countable family, it never says that it is a countable infinite family. So we could say that this is a countable family that we want. And then it is clear that V is covered by this thing, and the volume of this is equal to 0, because the general blocks have a 0 volume, so this will always hold. So we could have done that, but well, continuing, we have the following corollary, which tells us that if we have some set or some random set, arbitrary, some fixed point, this is a set in Rm, and this is a vector in Rn, so we can have that product between those, and this product will have n plus n measure 0. So this the proof of this is the following. So suppose that we have some covering of X, some countable covering by closed cubes, and this always work regardless of what X is, because for every X in X we can cover quotation mark cover X inside a cube, and the cube will of course be something like X minus epsilon X plus epsilon, and like this, right? So we can do that, and then X will be we call this Cx. This will be inside this, and this is an arbitrary union. Well, instead of close, it should be open, 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 like that. And then Lindelof theorem tells us that there exists a countable subcover of this arbitrary cover, but then this is open countable cover, but we can make this into a closed cover by taking its closure. So this is the justification of this step. Alright, but then we have that a cover of X times P is this family. This is a degenerate block, but then we saw previously that this is a set with m plus n measure 0, and this is a countable union of set with m plus n measure 0, so this has n plus n measure 0, and this is a subset of a set with m plus n measure 0, so it also has n plus n measure 0, so that proves that corollary. And now we have a proposition. We can prove this pretty easily. You just need to look for a contradiction. So the contradiction will be that X has n measure 0, but its interior will be non-empty. So there's a point inside X, so there exists some point, let's say x naught inside X, such that there also exists some delta positive, such that this is inside of X, but this doesn't have n measure 0. doesn't have n measure 0. It's well, it has a positive measure, a positive Lebesgue measure, but it doesn't have n measure 0 because its volume is positive. Its volume is positive. So we can have that inside of X there is set without n measure 0, because if you assume that X has n measure 0, then every subset of it has n measure 0. But this subset in fact doesn't have it, so this is a contradiction. And then we have that the interior will be empty necessarily. So moving on, we have this proposition about locally Lipschitz function. If X has n measure 0 and f is locally Lipschitz in X, then the image of this function also has n measure 0. This is interesting. And I need you to remember that a function is locally Lipschitz if we say that for every x in X, there exists some neighborhood of X such that the function restricted to this neighborhood is Lipschitz, right? So to start, let's consider, or let's analyze what happens when f is Lipschitz. Yes, Lipschitz is Lipschitz in X. So there will exist some constant k such that for every x in X, well, this is just absolute value, will be less or equal to k times this, right? So given that X has n measure 0, then X can be covered by, I mean, for every epsilon, there exists a cover of X such that the series of volumes of ck is less than any epsilon. But in particular, we can take epsilon divided by the root of m times k, all of this to the power of m. So let's say that, let me add a page. Let's say that we have some, this is the length of edge of the m cube ck. So this is, let me draw a cube here. So this is this length. All right. So it will happen that for every these pairs of elements inside the image of this set, there will exist inside this just by definition of functions, but then it also holds that for every I, the absolute value of the difference of these projections is less or equal than, well, this absolute value here. Well, we are on a vector field, so this should be the norm. It's not the absolute value, it is a norm. All right, so this is, and this is equal to and this, but then given that this function is Lipschitz, then this is more or equal than this part here. And then given that x and these values are inside this m cube, then this is less than the diameter of this cube. So it follows that this set here, let me highlight it here, this set here can be covered, or well, it is contained inside this cube of h. And why is that? Because we can take this as the length of the side of the cube, because these are constants that don't depend on x or y or whatever. So we can cover that set with this cube. All right, so next we say that we can write the whole image as x intersected with these sets, because as I told you, this was a covering of x. So this intersection is just equal to x, and then this is equal to the union of x intersected with this. But you know that the image of functions behaves fairly well with these unions. So this will be just equal to that, and then you know that they are covered by this. So this is inside these cubes of length, or well, of this here. But then you know that the volume of this is equal to, you know, the volume of a cube is its h to the power of m. So this will be, and then these are constants, you can take them outside, and inside of this will be, and this is equal to the volume of ck, because well, I said it here, yeah. This is the length of the cube. So this is the volume of ck, and then this is less than epsilon, because you know the series of these volumes was really less than epsilon divided by that, and we have that number multiplied by the epsilon divided by that, so it cancels out and we have this. But this works for Lebesgue function, and we are considering a general case of locally Lebesgue functions. So let's see what happens when we make it local. Let's say that for every x, just by definition of local Lebesgue function, you have that there exists some neighborhood of this x such that this is Lebesgue. Right, so we can say that x is covered by this open cover, but then we apply Lindelof and x will be covered by a countable family like that. So we apply f here, then the image of f will be inside. Once again, because images work fairly well with unions. I mean, like that. because the image of V is equal to the image of X intersected with V, because for the points of V that are not included in X, it's just the same. But then this set has n measure 0. So this is a countable union of set with n measure 0. So this also has n measure 0. And so that proof it's. And now the last theorem, just to complete all of these results, is the following. So we have some open set inside the RAM, and we have a function that is continuously differentiable on this open set, but into that are p, and p is more strictly more than m. So we will need to prove that the image of f has p measure 0. So this is interesting because if we are, let's say, on a plane, and we an open set of a plane, let me try it more nicely, and we take it to, I don't know, R3. So whatever, so this is continuously differentiable. So whatever this image is, it will have, in this case, 3 measure 0. And it makes a lot of sense because, this could be a surface or something like that, but all of them have a 3 measure 0. So you cannot make a volume here. You cannot make something with an empty interior here. It cannot be done because otherwise f couldn't be continuously differentiable. So it is an important theorem both for real analysis and for differential geometry, in fact. And the proof is as follows. Let me add a page here. So let W be equal to U times Rn minus, well, P minus M. This is a subset of Rp because this is inside Rm. So this is inside Rp, and we can define a function on W into Rp as this function, and this is equal to f of x. So it doesn't matter this variable, right? So it is obvious that this is continuously differentiable on W because f it is continuously differentiable, and also the image of this is equal to this, right? Because it doesn't matter what is in y in the second variable. So you can pick 0, and this has n measure 0. And I didn't tell you, but the functions that go from, in this case, Rp into Rp that are C1, or on a subset of Rp that are C1 are always locally Lipschitz. So we can apply that previous theorem that we saw, and then this image will be n measure 0 because G is locally Lipschitz and this has n measure 0. So that proves this final proposition, and this will be it for today. If you have any questions, you can write it down in the comments below, and I will try my best to answer them. Also, if you found this video interesting, please consider giving a thumbs up and subscribing to my channel. This will be it for today, and see you around.